Okay, again the shear is equal to 0. Okay, so what does positive and negative means, right? So down here, the case before, everything is positive. Okay, so everything is on the right hand side from the 0, right? So everything is in tensile. Okay, so on the other case, the second case that we have, not everything is in tension. We have a case that is a surface that's in tension, and the other surface which is in compression. Okay, so we are going to draw a Mohs circle. So I'm going to draw a bigger Mohs circle because I need to do a bit of laboring down here. Okay, so this is our so this is our normal stress. And over here, this is our shearing stress. Right? And then clockwise rotation of the element and anti-clockwise rotation element. So as I was saying earlier, right, over here on the right hand side, everything is in tensile. And then on this side, on the other side, everything is on compression. So one is positive, the other one is negative. Okay, so I will have a case where we know that stress X is in tension, right, or tensile. So this is where stress X will lie. So stress X will lie anywhere down here. Okay, so this is my stress X line. And then stress Y will be over here. Right, so this is our stress Y. Okay, so again, good practice is to label this as this on the element is your point X on Mohs circle. On your element, this is your point Y on Mohs circle. Okay, so as usual, the shearing stress is equal to 0. Okay, so because the shearing stress is equal to 0, the only place that shearing stress is possible to equal to 0 with a normal stress is that point over there. So this is my point X, and the other one over here, this is my point Y. Okay, so once again, we can construct a Mohs circle. Okay, we can construct Mohs circle, right? So we are going to draw a Mohs circle. Okay, there we are. So I'm going to introduce you to another term again. Okay, I'm going to introduce you another term. So at this point, okay, I'm going to draw the center of the circle first. So I'm going to construct a center of circle. Right, so as I mentioned before, this point over here is your point O, right? And then the distance from the 0 line, okay, 0 normal stress to here, this is your stress average. Okay, that is your average stress. So what we observe, I'm going to draw a horizontal line at the tip of the circle. Okay, so this is the tip of the circle. And then this distance over here, this is known as your tau max. Okay, so tau max it represents the maximum shear stress.
Eugene,
Yes.
is the average stress always the, is it always going to be the distance
Center.
from the 0 point on the graph to the 0 point on the circle?
Yes, it's always from 0 stress. Okay, 0 normal stress. Christian, make sense?
Yep, thank you.
Okay. Then from here, right, I'm going to introduce you to 2 more new terms. Okay, so I'm going to call this stress 1. This point over here is known as stress 1, and this point over here is known as stress 2. Okay, So stress 1 and stress 2. Okay, are known as.
Professor,
Yes.
in on the x-axis on the stress average, what is the double circle that you
0. O.
zero?
Point. Like that. O and a point. Hello?
Okay.
Okay, it's not a bullseye, okay? Are known as the principal stress. Okay, they're known as the principal stress. So the principal stress is usually where, right, the shear is equal to 0, right? If you look at stress 1 and stress 2, the shear stress is equal to 0, right? So tau max, now if you look at tau max, right? If you look at tau max is actually the what? Radius of the what? Right? Is the radius of the circle, right? If you look at it, tau max is the radius of the circle. Now, anyone can tell me why stress 1 is on the left-hand side, stress 2 is on the right-hand side? Anyone?
Because one was in compression and the other wasn't.
Okay, so does not matter. Okay, you can call this does not matter. Okay, you can call this stress 2 and you can call this stress 1. Is perfectly fine. Okay, so does not matter. Okay, if you want to call the left-hand side like why am I known as Eugene? Okay, mommy and daddy feel that it's a name. Okay, good, go for it. Right, there's no reason for it. Okay, so some of you do, but mine there's no reason. Okay, so if you look at the formula for stress 1 and 2, right, it's equal to the center of the circle plus or minus by the radius of the circle. Okay, so this is equal to stress average plus or minus by tau max. Okay, so later on, I'll teach you how to find tau max, which is really straightforward. Okay, right. So this is what the normal stresses will do to your Mohs circle. Okay, so these are the normal stress. Okay, so the next one, you all need time to copy, or we are good to go. Anyone? Are we okay? Wait, I have a question and I did not read earlier. I do apologize. What is that question on? Will shear stress be on the final? Based on the problem, I guess so. Oh, never mind. Okay, Louis. Yeah. It depends on the question. Okay. It depends on the question. Do you need to still know your shear stress? But you should. Okay. Right. So I have no question that I can see. Right. I'm going to go for the next page.
Actually, sir, I have a question.
Yes.
You said for stress 1 and 2, it's center of circle plus or minus radius.
Yes.
If the radius is equal to tau max, why is center of circle equal to average?
The center of the
Average stress.
circle and the radius are not the same thing, right? It's a center point.
No, I mean the radius and tau max are the same thing.
Yes.
So, but center of circle and average are not the same thing.
Not the same thing. You
But
can
they're
see
both
down.
equal to
Then
stress 1 and 2.
sometimes they can be equal, but sometimes they cannot be equal. They are not equal. Like for this case, the stress average magnitude, you see the yellow thing I'm highlighting?
Yes.
Is that distance? Oh no, only, right? But when look at the tau max down here, is this distance, right? So it's not the same,
Okay.
right? It's not always, it's not some, and in a situation it can be the same, okay, when one of the stress is equal to 0. Okay, you will see that later. Yeah, right. The next one that we are going to do, okay, the next one that we're going to look at is known as shearing stress. Okay. Now, shearing stress is a bit abstract, like the shear force, okay? Yeah, so let's look at shearing stress. So shearing stress are stresses acting parallel, okay, acting parallel to the surface. Okay. So what are the contribution of shearing stress? There are two, but we only have learned one in this course because of time. Okay. So what are they? Okay. So one is induced by shear force. Which is equal, so the shear is equal to VQ over IT, right? So this is what we learned that we have tested in term test 1, right? The other one is due to torsion. Okay, the other one is due to torsion, where the shearing stress is equal to TR over J, right? And T correspond to the torque. R is the radius of the shaft. And J is the polar second moment of area. Okay, so you have to combine both of them together, right? So the shearing stress is equal to VQ over IT plus PR over J. Okay, so this is the final form of the equation. Okay, unfortunately for this course, okay, we did not have time to go to torsion. I will not include TR over J at all. We're only going to deal with VQ over IT. Okay, right. So let's look at Mohs circle now. Okay, let's look at the element and Mohs circle. Okay, let's look at an element and Mohs circle now. How are they linked together? Okay, and then I will go slow on this. Okay, and you know, a piece of advice now: if you guys are copying, stop, don't copy. Okay, just listen to me and make me repeat 10 times. I don't care. Okay, because the confusion is always on the shearing stress side. Okay, normal stress, straightforward. We are good to go. It's the shearing stress that most of the time a lot of students are confused. And when I was a student, I thought it does not matter. Okay, it does matter. Okay, I thought as long as the magnitude is good, we're good to go. No, it does matter. Okay, okay, it does matter when we are designing with materials that has direction. Okay, so for example, carbon fiber, it's directional. If it's concrete, does not matter. But if it's reinforced concrete, it does matter again. Okay, so I see a question coming on me, and yeah, stop copying now. I want you all to listen. More important, okay? Because all this is available online. But later on, you want to copy again. It's up to it's okay. Okay, but I want you all to listen. Okay. So the first thing I'm going to draw transformation. So there are two types of shear. Okay, there are two types of shear. Okay, so the first type, which I'm going to do down here, I'm going to do first, which is your positive shear. Okay, and then later on, I'm going to do negative shear. So this is X and Y. Okay. Right. So over here, in shear, we say it's acting parallel, yes or no? So positive shear, it acts like this. Okay, so this is positive shear, right? So the shear for this case is shear XY. On the other side is shear YX. Okay, and I'll tell you why is it named this way.